My name is Juejun, and I'm an associate professor at the Department of Material Science and Engineering at MIT. Today, I'll present the talk at SENSE.nano symposium on the topic of imaging through flat fisheye lenses. So the topic of my talk today will be on the applications of new optical elements in biomedical imaging. Before I go into more technical content, I want to first thank my team who has contributed to this research. So the experimental demonstration of the meta lens is actually done by my postdoc, Mikhail Shalakino, and the theoretical design is done by Dr. Tian Gu, as well as my grad student, Feng Yang. The work is also done in close collaboration with Professor Hualang Zhang's group at UMass Law. So the motivation for this work is to look for new optical devices that can enable imaging with high optical quality, at the same time offering a wide field of view. The conventional solution to enable such wide field of view imaging is to use a kind of element that's called fisheye lenses. In a conventional fisheye lens, you need to stack together anywhere between 5 to 10 optical elements, such that any optical aberration at large field angles can be suppressed. The challenge, however, is that such imaging instruments becomes large, expensive, and also it's complicated to assemble. The solution we're trying to solve here is to use a new kind of devices called optical metasurfaces. To understand how the metasurface operates, we can consider a conventional lens like what I'm illustrating in this slide here. For conventional lens, when the light comes in, the curved surface is then going to refract and modify the propagating direction of light, then allowing them to focus onto the focal spot. Alternatively, you can also view the operation of lens as creating a phase delay profile, like what I'm illustrating here, such that the wavefront that allows light to converge into one focal spot. Optical metasurfaces are kind of devices where we can now fabricate on a flat substrate an array of subwavelength scale antennas. If we design the geometry of the antennas properly, then they will be able to impart phase delays that closely approximate the continuous optical phase delay profile in the case of conventional lens. Now, suppose the size of the antennas or the meta atoms are smaller than the wavelength, then what light sees will be effectively the same phase profile as in the case of conventional lens, and therefore it will then act as a focusing lens. This is what we call the metasurface lens or the meta lens. A simple meta lens structure, while it can help to improve the performance and at the same time reduce the size and weight of conventional optical systems, it does not, however, automatically lead to increased optical field of view. So this is illustrated in this simulation here. We are looking at a single layer of metasurface acting as a lens. And as we can see from the figure on the right side, when you actually increase the angle of incidence, the aberration of the lens increases, leading to severe distortion of the focal spot and compromised imaging quality. So that's why we have decided to look at a new architecture to enable wide field of view imaging using a metasurface lens. So the architecture is illustrated in this graph here. Essentially, we transform a flat piece of transparent glass into a fisheye lens that enables capturing of light across almost the entire 180-degree hemispheric field of view. So according to our design, we have a flat piece of substrate. We then pattern on the front side an aperture stop, such that light comes in from different angles, then refract on the front surface, and then impinge at the backside surface at slightly different locations. Now on the backside of the substrate, we then fabricate our metasurfaces, and what we show is that we design the phase profile properly, then light coming in at different angles, they can all be focused sharply onto one single image plane with high quality. Now, what I want to mention though is that this combination of aperture along with a refractive surface is actually non-new. And in fact, if you look back, this is some papers going back to the 1980s. People have already looked at combining this architecture with aperture along with a refractive surface. But the prior work were only able to expand the field of view up to about 30 degrees. So the question is, can we leverage this architecture to further enhance the field of view and resolution of existing lenses? So this is something we set out with up here. So we started out by trying to derive a new analytical formalism for wide field view flat lenses. So what I'm illustrating here is a generic configuration of the lens where we have a flat piece of glass with a thickness L, and then this supposed to focus the light to a focal plane I'm illustrating here. Now, if we look at light rays coming in at the same angle, but in just slightly different locations on the aperture, then according to the basic principle of optics, if you want to get a sharp focus, then the optical path length of the light rays going through these two different locations must be the same when they arrive at the imaging plane. So using this condition, we can then get one equation that constrains the phase profile of the metasurface. Now, if you look at the second graph here, we consider now two bundles of light rays that comes in at slightly different incident angles. And as a result, they will pass through the same region of the metasurface, but then now they are focused at different spots on the image plane. If we consider the phase profile of the meta lens, because both rays are focused at the same metasurface area, they should experience the same phase delay, provided that the angular dependence of the phase delay is negligible. This will allow us to come up with a second equation, and if we combine both equations together, then this yields an integral form of an analytical solution to enable wide field optical imaging. Now, based on this new theoretical insight, we then proceed to design a wide field view metasurface lens. So the performance of the lens is illustrated in this graph here. Across close to the entire 180-degree field of view, we see the lens maintains a high focusing efficiency of about 75%, and it also maintains high focusing quality, which is characterized by this parameter called the Strel ratio here. And the Strel ratio about 0.8 is usually considered as diffraction limit. So in this design here, we see the lens consistently maintains the diffraction limit performance across the entire 180-degree field of view. And this is clearly illustrated also in the focal spot profiles I'm showing on the right side here. Our next step is then to implement such a theoretical design into a practical experiment. So in our experiment, we started out by selecting an array of antennas or method atom geometries that then allows us to cover the full 360 degree of optical phase, 2 pi phase, and at the same time maintain a high optical transmission efficiency. The antennas then assumes the shapes of letter H as well as this rectangular geometry, and then these meta-atoms are then fabricated using a standard lithography on a transparent substrate. Once the lens is fabricated, we then proceed to characterize its optical performance. So in this slide, I'm showing you the measured profile of the focal spot at different incident angles, up to 85 degrees. The quantitative measurement has shown that the Strel ratio of lens is consistently above 0.8, which is in excellent agreement with our design, and also indicates that our lens can actually achieve a diffraction limited focusing performance covering an entire 170-degree field of view. We also measure the focusing efficiency of the lens, and the experimental results shows that the lens has a focusing efficiency of around 40% across the field of view, which is lower compared to a theoretical value of 75%, but it can be further improved with a reduced fabrication error. Finally, we want to test the imaging performance of such a wide field view meta lens. So what I'm showing you here is actually images we have taken using essentially a metasurface microscope, where we use the meta lens as the objective lens. So the image here is taken on a standard USAF resolution target that consists of a number of bars with well-defined spacing and width. So if the image can clearly resolve these bars, it means that we have reached the specified resolution. You may also notice that for instant angles above 50 degrees, the images are apparently stretched along the horizontal direction. I want to emphasize that this kind of distortion is actually inevitable, because what we're trying to do is that we're trying to map essentially the scene from a hemispheric field of view onto a planar imaging array. And as a result, inevitably, geometric distortion must be introduced. But the key takeaway message is that despite this distortion, the resolution of the lens is not compromised, and we can still clearly resolve all these resolution targets, indicating that the lens can achieve a resolution very close to the theoretical limit. So just to sum up, what I present to you is a new meta lens design that enables us to transform a flat piece of thin glass into a fisheye lens that offers diffraction-limited performance across near 180-degree field of view. So besides this ultra-wide field of view and high resolution enabled by diffraction-limited performance, the lens also features a compact form factor because it consists only one single piece of glass. It is lightweight, and it can also be manufactured in a scalable manner by leveraging standard silicon microfabrication techniques. So we also anticipate that this lens will also have a cost advantage compared to conventional multi-lens assembly. So after we have publicized this work, we have actually attracted a lot of attention from the community, and the work was also selected as top 10 research at MIT in the year of 2020. So now let's take a look at what are the applications of this meta lens technology. So it can be used as a powerful imaging instrument, and also because of reciprocity principle in optics, we can also use the meta lens in the reverse manner and use it as a way to realize wide-angle image projection. So that's why we foresee that this technology can be very useful for applications ranging from 3D sensing to near-eye display, as well as eye tracking and eye. Okay. That's why we foresee that this meta lens technology can find numerous applications ranging from 3D sensing to eye tracking and near-eye display. Now, because of the theme of this symposium is to discuss about biomedical applications, we'll specifically focus on some potential application examples in medical imaging domain. So our first example here is for endoscopic imaging. So what I'm illustrating on figure on the left-hand side here is a design example of a so-called wide-field view endoscopic lens. To enable high resolution as well as wide-field imaging, endoscopic lens typically has to use a multi-lens assembly, like in this case, with 5 individual elements, or introducing optical elements using gradient index technology. So if you look at the performance of this 5-lens assembly here, we have actually designed a fisheye meta lens to actually, with the same f number, but offering an enhanced field of view, a reduced track length of almost cut in half, and at the same time, improved resolution compared to the conventional refractive lenses. So this design example illustrates that our technology can potentially offer endoscopic imaging instruments with enhanced field of view, improved resolution, and also at the same time with a much compact footprint, which is critical for endoscopic imaging. I do want to mention one potential limitation about this meta lens technology here. Just as any other kind of metasurfaces, a meta lens design usually is chromatic, means that it operates best with a narrow band or single wavelength source. So when it comes to medical imaging applications, its performance could be maximized when operating with an active illumination by a light emitting diode or LED source. I also want to mention that it is actually possible to realize broadband operation of the metasurface technology. While there are some trade-offs we will have to pay, some penalties we have to pay here, right? We need to take a hit in terms of either the efficiency, the aperture size, or the F number. Okay. So besides the endoscopic imaging, our second example here is for retina imaging or fundus photography. So the photo on the right side shows you an example of a benchtop fundus camera system that is used to capture images of the retina from a patient. Now, conventional fundus camera, they have fairly limited field of view that does not allow the capturing of the entire retina in one single image. So later on, people have developed so-called wide field imaging systems that has a field of view exceeding 50 degrees. And more recently, state-of-the-art retina imaging systems can even offer field of view exceeding 180 degrees using the so-called ultra-wide field view technology. Now, this wide field view imaging methods, they are all built on the so-called confocal laser scanning technique, which is not only complicated, has a large footprint, but it also comes with a significant price tag. So in our case, if we apply our meta lens technology, we can actually realize a single piece of optical element with high resolution, and at the same time offering a comparable 180-degree field of view compared to current ultra-wide wide field imaging systems. So simply put, we may be able to offer a new retina imaging instrument that offers ultra-wide field of view, high resolution, and compact form factor with low cost. So with that, I want to summarize here, and I have presented to you a technology that enables a compact, lightweight, high resolution, as well as wide field view imaging solutions with a low cost. And we believe that this technology can potentially have significant applications in the field of biomedical imaging. So if there's any interest So if you have any potential interest in collaborations along this exciting applications, I will be more than happy to discuss with you about further synergies. Thank you.